A wound has opened on the sun. December 2025. Winter solstice. 62 times the diameter of Earth. Scientists call it a coronal hole. But that is just the beginning. Through this opening, a river of charged particles races toward our planet at over 1 million miles per hour. Auroras dance across skies that have never seen them, and deep beneath our feet, something may be stirring. 2025 is already one of the most seismically active years on record. New research suggests the sun and earthquakes may be connected in ways we are only beginning to understand. The Carrington event of 1859 crashed telegraph systems worldwide. A storm of that magnitude today could knock out power for months, damage satellites, and cost trillions of dollars. NASA's Parker solar probe just flew closer to the sun than any object in human history. 430,000 miles per hour through temperatures of 1800 degrees. What it found is rewriting everything we thought we knew about our star. The sun is not quiet, the sun is not predictable, and the sun is pointed directly at us. Can we survive what our star might send our way, and who will pay the price if we cannot? Chapter 1. The Dark Wound on Our Star. But before we begin, do not forget to subscribe, and if you truly enjoy these videos, please leave a like. Let us begin. December 2025. The winter solstice. Half the world tilts away from the sun, wrapped in the longest night of the year, and somewhere above us, 93 million miles away, something strange is happening on the surface of our closest star. A wound has opened. Not a wound of blood or flesh, but a wound of absence. A vast dark region stretching across the face of the sun, visible only through specialized telescopes that capture ultraviolet light at 193 angstroms. To the untrained eye viewing these images, it looks like someone has torn a hole straight through our star. The darkness spreads from the northern hemisphere, slices through the solar equator, and plunges deep into the southern regions. Scientists call it a coronal hole, and this one, emerging in the final weeks of 2025, is among the largest observed in the 21st century. The numbers are staggering. 500,000 miles across. That is roughly 62 times the diameter of Earth. You could line up our entire planet 62 times and still not span the width of this dark void. Yet calling it a hole is somewhat misleading. The sun has not actually developed a gap in its surface. What we are witnessing is something far more fascinating and far more consequential for everyone living on the third rock from the sun. To understand what a coronal hole truly is, you must first understand the sun itself. Our star is not a solid ball. It is a churning sphere of plasma, a fourth state of matter where temperatures are so extreme that atoms lose their electrons and become electrically charged particles. At the core, where temperatures reach 27 million degrees Fahrenheit, hydrogen atoms fuse into helium, releasing the energy that powers all life on Earth. But the story of coronal holes begins much further out, in the outermost layer of the solar atmosphere called the corona. The corona is a region of contradiction. While the surface of the sun sits at roughly 10,000 degrees Fahrenheit, the corona somehow reaches temperatures of 2 to 3 million degrees. This mystery puzzled scientists for decades. How could the outer atmosphere be hundreds of times hotter than the surface below it? The answer lies in magnetic fields, those invisible lines of force that thread through the sun like a vast three-dimensional tapestry. When these magnetic field lines twist, snap, and reconnect, they release tremendous energy that heats the surrounding plasma to extraordinary temperatures. In most regions of the corona, these magnetic field lines form closed loops. They arc up from the solar surface, curve through space, and plunge back down again. The superhot plasma follows these loops, trapped by the magnetic architecture, glowing brightly in ultraviolet light. But in a coronal hole, something different happens. The magnetic field lines do not loop back. Instead, they stretch outward, extending deep into space like highways with no return. The plasma that would normally be trapped can now escape, flowing outward along these open magnetic channels at tremendous speeds. This is why coronal holes appear dark. They are not empty. They are depleted. The hot, glowing plasma that normally fills the corona has fled. Streaming away from the sun as what we call the solar wind. What remains is cooler, less dense, and far dimmer than the surrounding regions. Through the specialized eyes of our space-based telescopes, these areas look like patches of shadow against the blazing face of our star. The coronal hole, now dominating the December sky, is what scientists call trans-equatorial. It does not simply sit near one of the sun's poles, as many coronal holes do during quiet periods. Instead, it cuts directly through the middle of the sun, crossing the solar equator like a dark river dividing two continents. This positioning matters enormously for Earth. Our planet orbits the sun along a plane called the ecliptic, roughly aligned with the solar equator. When a coronal hole opens near the poles, the high-speed solar wind it releases shoots off into space at angles that largely miss our world. But when a trans-equatorial hole opens and rotates to face Earth, we find ourselves staring directly down the barrel of a plasma cannon. The high-speed stream emerging from this December coronal hole travels at roughly 500 kilometers per second. That is over 1.1 million miles per hour. At this velocity, the solar wind reaches Earth in approximately 2 to 3 days, far faster than the normal solar wind that flows past our planet at more leisurely speeds. When this fast stream collides with our magnetic shield, the magnetosphere, the impact triggers what we call a geomagnetic storm. Right now, as you watch this video, instruments around the world are detecting the effects. Magnetometers in northern latitudes record fluctuations in Earth's magnetic field strength. The KP index, a measure of geomagnetic disturbance, scaled from 0 to 9, climbs to 5 or higher. The aurora oval, that ring of dancing lights encircling the polar regions, expands southward. People who have never seen the northern lights suddenly spot them from their backyards in Montana, Washington, and the upper Midwest. But the beauty masks potential danger. Our modern civilization runs on systems exquisitely vulnerable to space weather. Satellites orbiting Earth experience increased drag as the upper atmosphere swells with energy from geomagnetic storms. GPS signals degrade as the ionosphere becomes disturbed. High-frequency radio communications used by aircraft over polar routes black out for hours. Power grids experience voltage fluctuations as geomagnetically induced currents flow through their long transmission lines. In 1989, a geomagnetic storm knocked out power across Quebec, leaving 6 million people without electricity for 9 hours. That storm rated moderate on the scale of historical events. The coronal holes appearing during this solar cycle are generating conditions that could exceed anything we have experienced in the modern technological era. What makes the current situation particularly remarkable is timing. We are currently in solar cycle 25, the 25th 11-year cycle of solar activity since astronomers began systematic observations in 1755. Every 11 years or so, the sun's magnetic poles flip, and activity builds from a quiet minimum to an explosive maximum before declining again. Scientists initially predicted that solar cycle 25 would be weak, similar to the underwhelming cycle 24 before it. They were wrong. By October 2024, the sun had reached what NASA and NOAA officially declared as solar maximum, the peak of the cycle. Sunspot counts had exceeded predictions by significant margins. The strongest solar flares, massive explosions that release energy equivalent to billions of nuclear bombs, erupted with surprising frequency. And coronal holes, which typically become more common and larger during the descending phase after solar maximum, began appearing at unusual sizes while we were still climbing toward the peak. The December 2025 coronal hole is not an isolated phenomenon. Throughout this year, a series of gargantuan coronal holes have rotated across the sun's face, each one spraying Earth with high-speed solar wind streams. Some researchers are now questioning whether we have entered a particularly active period that could persist for years, perhaps continuing through the descent towards solar minimum around 2030. The implications extend beyond flickering lights and degraded GPS signals. Emerging research suggests connections between solar activity and processes deep within our own planet. Studies published in Nature and other prestigious journals have found statistically significant correlations between proton density in the solar wind and the occurrence of large earthquakes worldwide. The mechanism remains debated, but the data is increasingly difficult to ignore. When the sun sends charged particles streaming toward Earth, something responds within the crust and mantle below our feet. 2025 has already proven to be one of the most seismically active years on record. Coincidence? Perhaps. But the timing of earthquake swarms with solar wind impacts has raised eyebrows among researchers willing to investigate connections that mainstream science once dismissed as fringe speculation. We are learning that we live not on an isolated world, but within the extended atmosphere of a dynamic, sometimes violent star. The coronal hole staring at us right now is a reminder that 93 million miles offers less protection than we might hope. The sun sneezes, and Earth catches a cold. The sun opens a wound in its corona, and our satellites wobble, our power grids strain, our auroras dance, and perhaps even our tectonic plates shift. In the chapters ahead, we will dive deeper into this celestial drama. We will explore exactly how coronal holes form and why they matter. We will trace the history of the 11-year solar cycle back through centuries of observation. We will follow the solar wind on its journey from sun to Earth and examine what happens when it collides with our magnetic shield. We will revisit the Carrington event of 1859, the most powerful geomagnetic storm ever recorded, and ask what would happen if such an event struck today. We will investigate the controversial but growing body of evidence linking solar activity to earthquakes. We will journey alongside NASA's Parker Solar Probe as it flies closer to the sun than any human-made object in history. We will stand beneath the aurora and understand the physics that paints the night sky in greens, reds, and purples. And we will look toward the future, asking what our stormy star has in store for a civilization increasingly dependent on technologies that space weather can destroy. The dark wound on our star is not closing. If anything, the patterns suggest more and larger coronal holes in the years ahead as we descend towards solar minimum. Each one will send its river of charged particles washing over our world. Most of the time, our magnetic shield will hold. The disruptions will be minor. The auroras will be beautiful. But someday, perhaps soon, a coronal hole or coronal mass ejection will prove too powerful to dismiss. Understanding what is happening 93 million miles away has become essential knowledge for a technological species. The sun gives us life. It can also remind us, with humbling force, that we remain small creatures on a small world, subject to the whims of a star that has burned for 4.5 billion years and will continue burning for 4.5 billion more. The wound is open. Let us learn what it means. Chapter 2. What is a coronal hole? The name itself seems to contain a contradiction. How can the sun, that blazing sphere of nuclear fire, have holes? The answer requires us to abandon our earthly assumptions and think in terms of magnetic fields, plasma physics, and the strange behavior of matter at temperatures beyond anything we experience in daily life. Imagine for a moment that you could see magnetic fields, not with your eyes, which detect only a narrow slice of the electromagnetic spectrum, but with some enhanced sense that reveals the invisible architecture threading through space. If you looked at the sun with such vision, you would see something extraordinary. Lines of magnetic force erupting from the surface, curving through the corona, and diving back down again in graceful arcs. These closed loops trap plasma like invisible bottles, holding superhot gases in place and causing them to glow brilliantly in ultraviolet and X-ray wavelengths. But in certain regions, you would see something different. Lines of magnetic force that do not loop back. Instead, they stretch outward, reaching toward the stars, never returning. These are the open field regions, and the plasma here is not trapped. It flows outward along these magnetic highways at tremendous velocities, leaving behind a region that is cooler, less dense, and darker than its surroundings. This is what we call a coronal hole. The term was not always in use. Early astronomers studying the sun had no way to see these features directly. The corona itself was invisible, except during total solar eclipses, those rare moments when the moon blocks the blinding solar disk and reveals the pearly white atmosphere surrounding it. Some eclipse photographs from the 19th and early 20th centuries hinted at darker regions near the poles, but without the ability to see in ultraviolet light, scientists could not understand what they were observing. The breakthrough came with the Skylab mission in 1973. For the first time, Astronauts and instruments above Earth's atmosphere captured soft X-ray images of the sun with unprecedented clarity. There, unmistakably visible, were vast dark regions in the corona. Today we observe coronal holes routinely using spacecraft like NASA's Solar Dynamics Observatory, the ESA and NASA joint mission SOHO, and the newer GOES satellites that monitor space weather for the National Oceanic and Atmospheric Administration. These instruments capture images at specific wavelengths, particularly around 193 and 211 angstroms in the extreme ultraviolet range, where the contrast between normal corona and coronal holes is most striking. The physics of why coronal holes appear dark is elegant in its simplicity. The closed magnetic loops of the normal corona trap plasma at temperatures of 1 to 2 million degrees Kelvin, and this superheated gas radiates intensely in ultraviolet wavelengths. But in coronal holes, where the magnetic field lines open into interplanetary space, the plasma is free to escape. What remains is cooler, typically 700,000 to 1 million degrees Kelvin. Still unimaginably hot by earthly standards, but cool enough and sparse enough to appear dark compared to the surrounding corona. Think of it like a pot of boiling water with a lid versus one without. The lidded pot traps the steam, keeping the contents hot and roiling. Remove the lid, and the steam escapes. The pot cools. The coronal hole is the region where the magnetic lid has been removed, allowing the solar atmosphere to vent into space. Coronal holes come in different varieties, and understanding these distinctions helps explain their varying impacts on Earth. The most stable and long-lasting are polar coronal holes. These form near the north and south magnetic poles of the Sun and can persist for months or even years during periods of low solar activity. Because they are located at high solar latitudes, the high-speed solar wind they produce generally misses Earth, which orbits in the plane of the solar equator. More troublesome for our planet are equatorial coronal holes, and, especially, trans-equatorial coronal holes. These form at lower latitudes and can span the solar equator entirely. When such a hole rotates to face Earth, which happens as the Sun spins on its axis once every 27 days, the high-speed solar wind streams directly toward our world. The fast solar wind from these holes can persist for days or even weeks as the hole maintains its position relative to Earth during each solar rotation. There is also a category known as satellite holes. These are smaller coronal holes at lower latitudes that maintain magnetic connections to the larger polar holes through narrow corridors of open field lines. Satellite holes can produce variable fast solar wind streams that repeatedly sweep across Earth, complicating efforts to forecast space weather. The size of coronal holes varies enormously. Small holes may span only a few tens of thousands of miles. The giant trans-equatorial holes that have dominated recent space weather news stretch 500,000 miles or more, large enough to swallow dozens of Earths. Generally, larger holes produce faster and denser solar wind streams, which in turn cause more significant geomagnetic disturbances when they reach Earth. Coronal holes are intimately connected to the solar cycle. During solar minimum, when the sun is quiet and sunspots are rare, large polar coronal holes dominate. The magnetic field of the sun during these periods is relatively simple, with clearly defined north and south magnetic poles. The open field regions cluster near these poles, and the resulting high-speed solar wind flows primarily toward the outer solar system rather than toward Earth. As the sun approaches solar maximum, everything becomes more chaotic. The magnetic field grows increasingly complex as new active regions emerge. Sunspots dot the solar surface. The polar coronal holes may shrink or fragment, but intriguingly, equatorial and trans-equatorial coronal holes can appear, sometimes reaching enormous sizes even as overall solar activity increases. This is precisely what has surprised scientists during solar cycle 25. The giant coronal holes appearing in 2024 and 2025 were not expected at this stage of the cycle. After solar maximum, during the descending phase, coronal holes typically become more common and larger again. As the magnetic field simplifies and the new polarity establishes itself at the poles, open field regions expand. This period, lasting several years as the sun transitions toward the next minimum, often produces recurring high-speed solar wind streams that sweep past Earth with each solar rotation. The solar wind itself deserves closer examination. This continuous outflow of charged particles, predominantly protons and electrons, was predicted by the physicist Eugene Parker in 1958. Many of his colleagues were skeptical, but measurements from early spacecraft proved him correct. The solar wind streams outward in all directions from the Sun, filling interplanetary space and creating what we call the heliosphere, a vast bubble of solar influence extending far beyond the orbit of Pluto. Not all solar wind is created equal. The slow solar wind, originating from regions of closed magnetic field, travels at roughly 300 to 400 kilometers per second. The fast solar wind, emerging from coronal holes, can reach speeds of 700 to 800 kilometers per second, or even higher. When these two streams interact, with faster wind overtaking slower wind ahead of it, complex structures called corrotating interaction regions form. These regions can enhance the geomagnetic effects when they reach Earth. The plasma emerging from coronal holes carries embedded within it the magnetic field of the Sun. This interplanetary magnetic field, as it is called, has polarity, meaning it points either toward or away from the Sun depending on which hemisphere of the Sun the wind originated from. Coronal holes also have polarity. A positive polarity hole has magnetic field lines pointing outward from the Sun, while a negative polarity hole has field lines pointing inward. When the polarity of the incoming solar wind opposes Earth's own magnetic field orientation, a process called magnetic reconnection becomes more efficient, transferring more energy into our magnetosphere and producing stronger geomagnetic storms. Modern instruments on spacecraft like SOHO's solar wind, ion composition spectrometer, and the Advanced Composition Explorer have allowed scientists to study the chemical composition and temperature of solar wind from different sources. Fast solar wind from coronal holes shows distinct signatures: lower ionization states, reduced heavy ion abundances, and velocity distributions that reveal the acceleration mechanisms at work near the Sun. The study of coronal holes has entered a new era with the Parker Solar Probe and Solar Orbiter missions. Parker has flown through coronal hole interiors during its close approaches to the Sun, providing the first direct measurements of plasma conditions in regions where fast solar wind originates. The spacecraft has detected structures called switchbacks, dramatic reversals of the magnetic field that suggest complex dynamics in the acceleration of solar wind. Solar Orbiter, with its suite of remote sensing instruments, has revealed small-scale jets called picoflares within polar coronal holes that may contribute to both the heating of the corona and the acceleration of the solar wind. Despite decades of study, mysteries remain. Why does the corona reach temperatures hundreds of times hotter than the solar surface? Exactly what mechanisms accelerate the fast solar wind to such extreme velocities? How do coronal holes form and evolve? What determines whether a coronal hole will remain stable for months or disappear within days? These questions drive ongoing research programs at observatories and space agencies around the world. Planned missions like NASA's Multi-Slit Solar Explorer, expected to launch around 2027, will study the corona using advanced spectrographic techniques to measure plasma temperature, speed, and turbulence at unprecedented resolution. Understanding coronal holes and the solar wind they produce is essential for predicting space weather with enough accuracy to protect our satellites, power grids, and astronauts. For those of us watching from Earth, coronal holes present a fascinating duality. They are absences, regions where something is missing, plasma that has fled, light that has dimmed, yet their effects are profoundly present. When a giant coronal hole rotates to face our world, we feel its influence in disrupted communications, stressed power systems, expanded auroral zones, and perhaps even trembling faults deep beneath our feet. The dark patch on the Sun is not truly a hole. It is a doorway, an opening through which our star breathes its atmosphere into space. And when that breath is pointed at us, we would do well to pay attention. Chapter 3: The 11-Year Heartbeat. Long before humans understood that the Sun was a star, long before we knew about magnetic fields or nuclear fusion, careful observers noticed something peculiar. Dark spots appeared on the face of the Sun, grew, shifted position, and eventually faded away. The Chinese recorded such observations as early as 800 BCE, Greek philosophers debated what these blemishes might mean for a celestial body thought to be perfect and unchanging. But it was not until the early 17th century, when Galileo turned his telescope toward the sun, that systematic study of sunspots began. What Galileo saw challenged everything Europe believed about the heavens. Dark patches, irregular in shape, moving across the solar disk as the sun rotated. Some lasted weeks before vanishing. Others appeared suddenly in regions that had been clear days before. The sun was not a flawless sphere of divine fire. It was dynamic, changeable, subject to forces no one yet understood. Over the following centuries, astronomers accumulated observations. The German pharmacist Samuel Heinrich Schwabe spent 17 years obsessively tracking sunspots, drawing the solar disk day after day between 1826 and 1843. His persistence revealed a pattern no one had suspected. Sunspot numbers rose and fell in a regular rhythm, peaking roughly every 10 years before declining to minimum levels. Schwabe had discovered the solar cycle. Further refinements pinpointed the average length at approximately 11 years, though individual cycles vary from as short as 9 years to as long as 13. The Swiss astronomer Rudolf Wolf standardized methods for counting sunspots and reconstructed historical records back to 1755, which marks the beginning of solar cycle 1. We are now in solar cycle 25, which began in December 2019 and will likely continue until around 2030. But what causes this 11-year heartbeat? Why does our star pulse between quiet phases with few or no sunspots and active phases where the solar surface erupts with dozens of dark patches, explosive flares, and billion-ton ejections of plasma? The answer lies in the sun's magnetic field and its extraordinary behavior. Unlike Earth, which has a relatively stable magnetic field generated by its solid iron core and liquid outer core, the sun generates its magnetic field through a process called the solar dynamo. The sun is not solid. It is a sphere of plasma that rotates, and it does not rotate uniformly. The equator completes one rotation in about 25 Earth days, while regions near the poles take closer to 35 days. This differential rotation stretches and twists magnetic field lines that initially run from pole to pole. Imagine taking a rubber band stretched between the top and bottom of a spinning sphere, then spinning the middle faster than the ends. The band would wrap around the equatorial regions, becoming increasingly wound and distorted. This is essentially what happens to the sun's magnetic field. Over years, the poloidal field, running from north to south, transforms into a toroidal field, wrapped around the sun's interior like coils around a cylinder. These concentrated magnetic field lines eventually become unstable. They rise buoyantly through the solar interior, puncturing the surface in paired loops that we observe as sunspot groups. Sunspots appear dark because the intense magnetic fields within them suppress convection, preventing hot plasma from welling up from below. The result is a region roughly 3,000 degrees cooler than the surrounding photosphere. Cool enough to appear black by contrast, though still blazing at nearly 7,500 degrees Fahrenheit. The magnetic polarity of sunspot pairs follows predictable rules discovered by American astronomer George Ellery Hale in the early 20th century. In each hemisphere, the leading sunspot in a pair, the one ahead in the direction of rotation, has a consistent polarity throughout a given cycle. The trailing spot has the opposite polarity. Furthermore, this orientation is reversed between the northern and southern hemispheres. If northern leading spots are positive in one cycle, southern leading spots will be negative. And here is where the story becomes even more remarkable. When the next 11-year cycle begins, everything flips. Leading spots in the north that were positive become negative. Southern leading spots switch from negative to positive. The sun's entire magnetic polarity is reversed. What was the magnetic north pole is now the magnetic south pole, and vice versa. This means that the true cycle of the sun's magnetic field is not 11 years, but roughly 22 years. After 2 activity cycles, the sun returns to its original magnetic configuration. This 22-year period is sometimes called the Hale cycle, honoring the scientist who discovered the polarity rules. Solar maximum refers to the period when sunspot numbers peak and solar activity is most intense. During maximum, the sun's magnetic field is chaotic, with field lines tangled across multiple active regions. Flares become frequent and powerful, Coronal mass ejections blast billions of tons of plasma into space. The corona itself changes shape, becoming more irregular as streamers and active region loops dominate the view. Solar minimum is the quiet phase. Sunspots may be entirely absent for weeks or months. The magnetic field simplifies, with clear polar regions of opposite polarity. Coronal holes expand near the poles. The corona takes on a more symmetric appearance. Solar flares and coronal mass ejections become rare. The transition from minimum to maximum takes approximately 4 to 5 years. Activity builds gradually at first, then accelerates. New sunspots appear at higher latitudes, then migrate toward the equator as the cycle progresses. A pattern visualized in what scientists call the butterfly diagram, because the latitude versus time plot of sunspot positions resembles a butterfly's wings. The transition from maximum back to minimum also takes several years, but tends to be more gradual. The descending phase is notable for the increasing prominence of coronal holes, particularly equatorial ones that can persist through multiple solar rotations. This is the period when recurring high-speed solar wind streams are most common, sweeping past Earth every 27 days as the same coronal hole rotates back into geoeffective position. Not all solar cycles are created equal. Some maximums produce far more sunspots and intense activity than others. Scientists use the smoothed sunspot number, a 13-month average that reduces short-term fluctuations, to compare cycle strength. The strongest cycle on record was cycle 19, which peaked in 1958 with a smoothed sunspot number exceeding 200. The weakest in the modern era was cycle 24, which peaked in April 2014 with a maximum around 116, well below the historical average of approximately 179. The prediction for solar cycle 25, released by an international panel convened by NOAA, NASA, and the International Space Environmental Services in December 2019, forecast another weak cycle with a maximum of about 115 sunspots around July 2025. This prediction fit within the trend of weakening cycles that had characterized cycles 21 through 24. Some researchers even speculated that the Sun might be heading toward a grand minimum, an extended period of very low activity like the Maunder minimum of 1645 to 1715, when sunspots nearly disappeared for 70 years. The prediction was wrong. By 2022, just 2 years into the cycle, observed sunspot numbers were already exceeding forecasts. Activity ramped up faster than anyone expected. By October 2023, NOAA issued a revised prediction calling for an earlier and stronger peak, possibly reaching smoothed sunspot numbers between 137 and 173, sometime between January and October 2024. In October 2024, NASA and NOAA officially declared that the Sun had reached solar maximum. The smoothed sunspot number had climbed to approximately 161. Solar cycle 25 was not just stronger than predicted. It had proven to be significantly more active than its predecessor. Cycle 24, the surprises continued. Even after the official declaration of maximum, activity remained high. In November 2025, the Sun unleashed an X5.16 solar flare, the strongest of the cycle and the sixth most powerful in all of solar cycle 25. Coronal holes that should have been more typical of the descending phase appeared at enormous sizes while the Sun was still near peak activity. Scientists now debate whether we have truly passed the maximum or whether solar cycle 25 might produce a secondary peak. Some cycles in history have exhibited double maxima, with 2 distinct peaks of activity separated by a year or more. The data through late 2025 shows hints that this could be occurring, though only time will reveal the true shape of the cycle. Why does any of this matter beyond academic curiosity? Because the solar cycle controls the rhythm of space weather that affects our planet. During solar maximum, geomagnetic storms become more frequent and more intense. The radiation environment in space becomes more hazardous for astronauts and spacecraft electronics. Satellite operators face increased drag and debris tracking challenges. Power grid operators must be vigilant for geomagnetically induced currents. Airlines reroute polar flights to avoid radiation exposure, and communication blackouts. Conversely, during solar minimum, the risks diminish but do not disappear. Cosmic rays from outside the solar system penetrate more easily when the sun's magnetic field is weak, slightly increasing radiation exposure at high altitudes. And the coronal holes that grow during the descending phase and minimum continue producing high-speed solar wind streams that can trigger geomagnetic storms. Even when the sun seems quiet, the 11-year heartbeat of our star is not merely an astronomical curiosity. It is a rhythm that shapes the space environment in which our entire technological civilization exists. Understanding it, predicting it, and preparing for its variations has become essential for a species that has wrapped itself in satellites, power grids, and global communication networks. The sun will continue pulsing through its cycles for billions of years to come. Our challenge is to learn its rhythms well enough to dance safely within them. Chapter 4: Solar Wind and the Invisible River. In 1958, a young physicist named Eugene Parker proposed something radical. He suggested that the sun was not simply radiating light and heat into an empty void. Instead, it was exhaling, continuously streaming charged particles outward at tremendous velocities, filling the entire solar system with a thin but constant flow of solar material. He called this flow the solar wind. His colleagues were skeptical. Some were hostile. The idea that plasma could continuously escape the sun's gravity and pervade interplanetary space seemed to contradict thermodynamic principles. One prominent scientist recommended that Parker's paper be rejected from publication, but the editor chose to publish it anyway, and within 4 years, the Soviet Luna 1 and American Mariner 2 spacecraft confirmed that Parker had been right all along. The solar wind is real. It is everywhere, and it fundamentally shapes the space through which all planets move. To understand the solar wind, you must first appreciate the extraordinary temperatures of the solar corona. While the visible surface of the sun, the photosphere, registers at roughly 5,500 degrees Celsius, the corona reaches temperatures of 1 to 3 million degrees Celsius. At such extreme temperatures, the thermal energy of particles exceeds the gravitational binding energy of the sun. They can escape, and escape they do, in numbers beyond ordinary comprehension. Every second, the sun loses approximately 1 million tons of material to the solar wind. That sounds like an enormous amount, and it is by any human measure, but the sun contains roughly 2,000 trillion tons of matter. At the current loss rate, it would take 150 billion years for the solar wind to carry away even 1% of the sun's mass. Our star can afford to be generous with its outflow. The composition of the solar wind reflects the composition of the sun itself. Approximately 95% consists of protons, the nuclei of hydrogen atoms. Another 4% comprises alpha particles, which are helium nuclei containing 2 protons and 2 neutrons. The remaining 1% includes heavier ions, electrons, and trace amounts of other elements. All of these particles carry electrical charge, making the solar wind a plasma, an electrically conductive gas threaded with magnetic field lines. Those magnetic field lines are crucial. As solar wind plasma streams outward from the sun, it carries embedded within it the magnetic field of the solar corona. This interplanetary magnetic field, often abbreviated IMF, does not simply point straight outward. Because the sun rotates while the plasma flows outward, the field lines curve into a spiral pattern, like water spraying from a spinning garden sprinkler. This is called the Parker spiral, named after the same Eugene Parker who predicted the solar wind. At Earth's orbit, 93 million miles from the sun, the Parker spiral makes an angle of roughly 45 degrees with respect to the Sun-Earth line. The magnetic field lines have wound around enough to be significantly tilted from the radial direction. This geometry matters because the orientation of the interplanetary magnetic field strongly affects how the solar wind interacts with Earth's magnetosphere. Not all solar wind travels at the same speed. Slow solar wind, typically originating from regions of closed magnetic loops near the sun's equator, moves at 300 to 400 kilometers per second. Fast solar wind, streaming from coronal holes where magnetic field lines open directly into space, can reach 600 to 800 kilometers per second, or even faster. At these velocities, it takes the slow solar wind 4 to 5 days to reach Earth. Fast solar wind can arrive in 2 to 3 days. When fast solar wind catches up with slow solar wind ahead of it, the two streams interact, creating compressed regions of higher density and stronger magnetic fields called corrotating interaction regions. These structures spiral through the solar system along with the Parker spiral and can enhance geomagnetic effects when they sweep past Earth. During the descending phase of the solar cycle, when coronal holes are common and persistent, corrotating interaction regions become a regular feature of space weather. The solar wind does not stop at Earth. It continues outward, past Mars, past Jupiter, past Saturn, beyond the orbit of Pluto, until it finally encounters the interstellar medium, the thin gas and dust between the stars. This boundary region is called the heliopause, located roughly 120 astronomical units from the Sun, or about 11 billion miles. Within this vast bubble, called the heliosphere, the solar wind dominates. Beyond it lies interstellar space, territory explored only by the Voyager 1 and 2 spacecraft. The solar wind creates and maintains this heliosphere, a protected zone within the galaxy. Cosmic rays, high-energy particles accelerated by distant supernovae and other violent events, constantly bombard the heliosphere from outside. The magnetic field carried by the solar wind deflects and modulates many of these cosmic rays, reducing the radiation environment throughout the solar system. When solar activity is high and the solar wind is strong, fewer cosmic rays penetrate to Earth's orbit. When solar activity is low, more get through. But it is the interaction with Earth's magnetic field that most directly affects human technology and safety. Earth is surrounded by a magnetosphere, a region of space dominated by our planet's magnetic field. This field is generated deep within Earth's core, where the rotation of liquid iron creates a dynamo effect, similar in principle to the Sun's dynamo, but operating on vastly different scales. The magnetosphere extends tens of thousands of miles into space on the day side, facing the Sun, and stretches into a long tail millions of miles long on the night side. When the solar wind arrives at Earth, it cannot simply penetrate the magnetosphere. Plasma cannot easily cross magnetic field lines. Instead, the solar wind flows around the magnetosphere like water around a rock in a stream. On the sunward side, it compresses the magnetosphere, pushing the boundary, called the magnetopause, closer to Earth. On the nightward side, it stretches the magnetosphere into an elongated tail. The pressure of the solar wind determines the position of the magnetopause. Under normal conditions, this boundary sits roughly 10 Earth radii from the surface, about 40,000 miles. During periods of high solar wind pressure, such as when a high-speed stream from a coronal hole impacts Earth, the magnetopause can be pushed inward to 6 Earth radii or less. Satellites in geostationary orbit, approximately 22,000 miles up, can find themselves momentarily outside the protection of the magnetosphere. The most significant factor in solar wind-magnetosphere interaction is not the speed or density of the incoming plasma, but the orientation of the interplanetary magnetic field. Earth's magnetic field points northward at the equator, from South Pole toward North Pole. When the interplanetary magnetic field has a southward component, opposing Earth's field, a process called magnetic reconnection can occur. Magnetic reconnection is a fundamental process in plasma physics. When two magnetic field lines of opposite polarity meet, they can break and reconnect in new configurations, releasing tremendous amounts of energy. At Earth's dayside magnetopause, reconnection between southward interplanetary magnetic field and northward terrestrial field opens a pathway for solar wind energy to enter the magnetosphere. This energy flows along magnetic field lines toward the poles, energizes particles in the radiation belts, and ultimately drives the phenomena we call geomagnetic storms. The KP index, mentioned in earlier chapters, is one measure of geomagnetic activity resulting from solar wind magnetosphere interaction. It is calculated from magnetometer observations at stations around the world, tracking fluctuations in the magnetic field caused by electrical currents in the magnetosphere and ionosphere. The index runs from 0, indicating very quiet conditions, to 9, indicating extreme storm levels. NOAA's Space Weather Prediction Center uses a simpler 5-level scale for geomagnetic storms, ranging from G1 for minor storms to G5 for extreme storms. Each level corresponds to specific ranges of the KP index and carries different implications for technology and infrastructure. A G1 storm might cause minor power grid fluctuations and slightly expand the auroral zone. A G5 storm could cause widespread power outages, damage transformers, disrupt satellite operations, and produce auroras visible from tropical latitudes. The solar wind is thus far more than an astronomical curiosity. It is a medium through which our star constantly interacts with our planet. Every moment of every day, Earth swims through this invisible river of charged particles. Most of the time, our magnetic shield deflects the flow with ease. But when the solar wind intensifies, when a high-speed stream from a coronal hole or a shock wave from a coronal mass ejection arrives, the interaction can become violent. Eugene Parker, who passed away in 2022 at age 94, lived to see his theoretical prediction confirmed beyond any doubt. He saw spacecraft venture into the solar wind and measure its properties directly. He witnessed the launch of the Parker Solar Probe, the first NASA mission ever named for a living person, which now flies closer to the Sun than any human-made object in history. The invisible river continues to flow. It has flowed for 4.5 billion years, since the Sun first ignited in the collapsing cloud of gas and dust that formed our solar system. It will continue flowing for billions of years more, until the Sun exhausts its hydrogen fuel and swells into a red giant, ultimately shedding its outer layers and becoming a white dwarf. For now, we learn to read the river's currents and predict its floods. The solar wind carries the breath of our star to every corner of the heliosphere. Understanding that breath and respecting its power is no longer optional for a technological civilization. It is essential. Chapter 5. When the Shield Falters. On March 13th, 1989, the Sun hurled a massive cloud of plasma and magnetic field toward Earth. The coronal mass ejection traveled through interplanetary space for 3 days before slamming into our planet's magnetosphere with devastating force. Within 90 seconds of the impact, 6 million people in Quebec lost electricity as the Hydro-Quebec power grid collapsed. Transformers overloaded. Circuit breakers tripped in cascading failures. The province went dark. For 9 hours, hospitals switched to backup generators. Traffic signals failed. Heating systems shut down on a night when temperatures plunged well below freezing. Schools closed. Businesses halted. A modern society discovered just how vulnerable it had become to events 93 million miles away. The March 1989 geomagnetic storm was severe, but it was not exceptional by historical standards. It registered approximately negative 589 nanoteslas on the DST index, a measure of the depression in Earth's magnetic field caused by ring current intensification during storms. This placed it among the strongest storms of the 20th century, but nowhere near the strongest ever recorded. That distinction belongs to events from an era before our technological dependencies made space weather a matter of critical concern. Yet even in 1989, the Quebec blackout demonstrated that modern infrastructure exists within the reach of solar fury. To understand how geomagnetic storms damage power grids and disrupt technology, we must examine what happens when the solar wind magnetosphere interaction intensifies beyond normal levels. Under ordinary conditions, Earth's magnetic field deflects most of the solar wind around the planet. Magnetic reconnection occurs at modest rates, and the energy entering the magnetosphere dissipates. But when a coronal mass ejection arrives, or when a particularly fast and dense solar wind stream from a coronal hole impacts the magnetopause, the dynamics change dramatically. Coronal mass ejections are fundamentally different from the steady solar wind. These are explosive releases of billions of tons of plasma and tangled magnetic field, blown outward from the Sun at velocities ranging from a few hundred to over 2,000 kilometers per second. The fastest CMEs can reach Earth in under 24 hours. A typical transit takes 2 to 3 days. When they arrive, they often carry magnetic fields much stronger than the ambient solar wind. And these embedded fields can be oriented strongly southward, maximizing the conditions for magnetic reconnection. The arrival of a CME at Earth occurs in stages. First comes the shock wave, the boundary where the fast-moving CME plasma has compressed the slower solar wind ahead of it. This sudden compression pulse causes what is called a storm sudden commencement, a sharp increase in the magnetic field strength recorded at ground stations worldwide. The magnetosphere is squeezed, and currents flowing in the magnetopores intensify. Behind the shock comes the sheath region, the turbulent zone of compressed plasma between the shock and the CME proper. Sheath regions often contain highly variable magnetic fields, including southward components that can drive reconnection and storm development even before the main CME structure arrives. Finally comes the magnetic cloud, or ejector itself, the core of the CME. This region typically shows smoothly rotating magnetic fields and lower plasma temperatures. If the magnetic field within the cloud is oriented southward for extended periods, it can drive prolonged and intense geomagnetic storming. As reconnection proceeds on the dayside magnetopores, magnetic flux is transferred to the nightside magnetotail. Energy accumulates in the tail until instabilities cause explosive reconnection there as well, releasing the stored energy into the inner magnetosphere. Particles are accelerated to high energies and injected into the ring current, a belt of charged particles encircling Earth at distances of 3 to 8 Earth radii. The ring current creates its own magnetic field, opposing Earth's field at low latitudes. This is what the DST index measures. During intense storms, the ring current can become so strong that it measurably reduces the surface magnetic field by hundreds, or even over 1,000 nanoteslas. The depression in field strength indicates the energy that has been pumped into the magnetosphere from the solar wind. Meanwhile, currents also flow in the ionosphere, the electrically conducting layer of Earth's upper atmosphere. Auroral electrojets, intense horizontal currents flowing in the auroral zones, can exceed millions of amperes during major storms. These rapidly varying currents induce electric fields at Earth's surface through electromagnetic induction, the same principle that makes transformers work. Here is where human infrastructure becomes vulnerable. Long conductive networks like power lines act as antennas for these induced electric fields. Currents called geomagnetically induced currents, or GICs, flow through the grounded neutrals of transformers, seeking paths through the power grid. These are quasi-direct current flows, very different from the alternating current the grid is designed to handle. Transformers are particularly susceptible. GICs can saturate transformer cores, causing them to operate inefficiently, generate excess heat, and produce harmonic distortions in the power signal. In mild cases, this simply degrades power quality. In severe cases, transformers can overheat and suffer permanent damage. The failure of even a few critical transformers can cascade through interconnected grids, causing widespread blackouts. The Quebec collapse in 1989 demonstrated this vulnerability dramatically. Within 90 seconds of the storm's intensification, relays tripped across the Hydro-Quebec system. The utility had no time to respond. The province's grid was down before operators fully understood what was happening. Recovery took hours. Had more transformers been permanently damaged, recovery could have taken weeks or months. Modern power grids have implemented some protections since 1989. Operators monitor space weather forecasts and can take precautions during predicted storms, such as cancelling maintenance, increasing reserves, and preparing for potential load shedding. Some utilities have installed GIC blocking devices on vulnerable transformers, but the fundamental vulnerability remains. A sufficiently powerful storm will overwhelm existing protections. Power grids are not the only concern. Geomagnetic storms affect satellites in multiple ways. Enhanced radiation levels can damage sensitive electronics and degrade solar panels. Increased atmospheric drag at low Earth orbit altitudes causes satellites to lose altitude faster than expected. Thousands of satellites now fill low Earth orbit, including mega constellations like Starlink. During the May 2024 geomagnetic storm, one of the strongest in decades, satellite operators reported significant increases in drag and the need for coordinated maneuvering to avoid collisions. GPS and other global navigation satellite systems rely on precisely timed radio signals passing through the ionosphere. Geomagnetic storms disturb the ionosphere, introducing errors that degrade positioning accuracy. During the 1989 storm, GPS errors reportedly exceeded normal levels significantly. Aviation authorities issued warnings about reduced navigation reliability. High-frequency radio communications, used by aircraft over oceanic and polar routes, can be completely blocked during major storms. When the ionosphere is severely disturbed, radio signals that normally reflect off this layer and travel beyond the horizon instead become absorbed or scattered. Aircraft lose contact with ground controllers. Emergency communications become unreliable precisely when they might be most needed. The radiation environment in space intensifies during geomagnetic storms. Particles accelerated to high energies can penetrate spacecraft shielding and damage electronics or pose radiation hazards to astronauts. During the largest storms, crew aboard the International Space Station may be instructed to shelter in more heavily shielded portions of the station. Future crewed missions to the Moon and Mars will need robust plans for dealing with space weather emergencies far from Earth's protective magnetosphere. Oil and gas pipelines, which can stretch for hundreds or thousands of miles, also experience geomagnetically induced currents. While pipelines are not as acutely vulnerable as power transformers, GICs can accelerate corrosion at points where the currents enter or exit the metal structure. Over time, repeated exposure to GICs can compromise pipeline integrity, potentially leading to leaks or failures. The interconnected nature of modern infrastructure creates additional risks. A power outage can cascade into water treatment failures, hospital emergencies, communication breakdowns, and transportation disruptions. Financial systems that depend on electronic transactions can be paralyzed. The downstream effects of a major geomagnetic storm extend far beyond the immediate electrical impacts. NOAA, NASA, the European Space Agency, and other organizations maintain fleets of spacecraft to monitor the sun and the solar wind, providing early warning of incoming disturbances. Satellites at the L1 Lagrange point, about 1 million miles sunward of Earth, can detect CME arrivals typically 15 to 45 minutes before they reach Earth. This warning time allows some protective actions but is far too short for many preparations. The goal of space weather research is to extend warning times and improve forecast accuracy. New missions, better models, and enhanced understanding of Sun-Earth connections all contribute to this effort. But the fundamental reality remains. Earth orbits within the atmosphere of an active star, and that star occasionally reminds us of our vulnerability, with storms that can overwhelm our shields. When the next great storm comes, will we be ready? The answer depends on investments we make today in monitoring, forecasting, and hardening our critical infrastructure. The shield has faltered before. It will falter again. The question is whether we will be caught off guard or prepared to weather the solar fury. Chapter 6. The Carrington Event of 1859. The morning of September 1st, 1859, began like any other. For Richard Carrington, the wealthy English amateur astronomer had built a private observatory at Redhill, south of London, where he pursued his passion for solar observation with the discipline of a professional scientist. Each clear day, he projected an image of the sun onto a screen and carefully sketched the positions and shapes of sunspots, building a record that would contribute to humanity's understanding of the solar cycle. Shortly before noon, as Carrington traced the outlines of a large sunspot group, something unprecedented happened. Two brilliant patches of white light erupted within the sunspot region, intensely bright against the already luminous solar disk. Carrington was so startled that he rushed to find a witness, but by the time he returned barely a minute later, the lights were already fading. The entire event lasted approximately 5 minutes. Carrington had witnessed the first recorded observation of a solar flare. He was not alone. Independently, another English astronomer named Richard Hodgson observed the same phenomenon from his own observatory. Both men published their observations in the monthly notices of the Royal Astronomical Society, their accounts appearing side by side in the November 1859 issue. They had documented something no human had ever recorded before, an explosive release of energy on the surface of the sun. But Carrington remained cautious about drawing conclusions. In his report, he noted that a significant magnetic disturbance had occurred on Earth the following day, but he wrote that one swallow does not make a summer. He suspected a connection but knew that a single coincidence did not constitute proof. What Carrington could not have known was that the flare he observed was associated with a massive coronal mass ejection, a billion-ton cloud of magnetized plasma that was already racing toward Earth at extraordinary speed. The CME reached our planet in just 17.6 hours, a transit time so fast that it remains exceptional even by modern standards. Typical CMEs take 2 to 4 days to reach Earth. The Carrington CME traveled at nearly 2,400 kilometers per second. When it arrived on September 2nd, 1859, the impact triggered the most intense geomagnetic storm in recorded history. The effects were felt worldwide. Telegraph systems, the cutting-edge communication technology of the era, went haywire. Operators reported sparks leaping from their equipment. Some received electrical shocks. In several offices, telegraph paper caught fire from the induced currents. Yet paradoxically, some telegraph lines continued to operate even after operators disconnected their batteries, powered solely by the geomagnetically induced currents flowing through the wires. One telegraph operator in Pittsburgh reported that the weights of his register were lifted by the strength of the current. Another in Boston found he could communicate with Portland, Maine, using only the auroral current, no battery required. Messages sent under these conditions were reportedly clear and readable. The Earth itself had become a power source. The auroral displays that accompanied the storm were perhaps the most spectacular ever witnessed by modern humanity. The northern lights, normally confined to high latitudes, swept across the entire northern hemisphere. Auroras were observed in Cuba, Hawaii, and as far south as Colombia and Panama. In the southern hemisphere, the aurora australis was seen from Chile, Australia, and reportedly from ships at sea near the equator. The light was so intense that people woke in the night believing dawn had arrived. In the Rocky Mountains, gold miners began preparing breakfast, fooled by the brightness into thinking morning had come. Newspapers reported that residents of the northeastern United States could read by the light of the aurora alone. The sky glowed in curtains of red, green, and purple, colors dancing and shifting in patterns that terrified some observers and enchanted others. Contemporary accounts describe the aurora as filling the entire sky, horizon to horizon. Some witnesses compared it to the sky being on fire. Others described sheets and curtains of light rippling overhead. The phenomenon persisted for hours, far longer than typical auroral displays, reflecting the sustained intensity of the geomagnetic storm. Scientific instruments of the era captured quantitative evidence of the storm's power. Magnetometers at observatories worldwide recorded extreme fluctuations. The Kew Observatory in London documented what is now interpreted as a magnetic crochet, a sudden disturbance in the magnetic field occurring simultaneously with the solar flare itself, caused by increased ionization in the upper atmosphere from the flare's X-ray and ultraviolet emissions. The main storm phase produced magnetic field depressions estimated at over 1,700 nanoteslas, based on reconstructions from surviving records. For comparison, the March 1989 storm that blacked out Quebec reached approximately negative 589 nanoteslas. The Carrington event was roughly 3 times more intense by this measure. Scientists have since studied the Carrington event extensively, attempting to understand what made it so extreme and what the consequences would be if a similar storm struck today. The emerging picture is sobering. The Carrington CME was likely preceded by another CME a day or two earlier. This prior eruption may have cleared the interplanetary medium of slower solar wind, allowing the Carrington CME to travel through a partially evacuated channel at exceptional speed. When it arrived at Earth, its magnetic field was oriented strongly southward for an extended period, maximizing the efficiency of magnetic reconnection and energy transfer into the magnetosphere. In 1859, the world's technological infrastructure consisted primarily of telegraph networks. These were vulnerable to geomagnetically induced currents, but the damage was limited. Operators could disconnect batteries and wait out the storm. Today, the situation is vastly different. Studies commissioned by the National Academy of Sciences and other bodies have attempted to estimate the impact of a Carrington-class storm on modern infrastructure. The results are alarming. Power grids across North America and Europe could experience widespread transformer failures. Unlike the Quebec event of 1989, where a handful of transformers failed and were replaced within weeks, a Carrington-level storm could damage hundreds of high-voltage transformers simultaneously. These transformers are not mass-produced items sitting in warehouses. They are custom-manufactured, often overseas, with lead times of 1 to 2 years. If hundreds failed at once, replacement would take years. Areas without power for extended periods would face cascading failures in water treatment, sewage systems, food distribution, medical care, and public order. The National Academy study estimated that a severe geomagnetic storm could cause economic damage exceeding $2 trillion in the United States alone during the first year. Recovery could take 4 to 10 years. Some researchers consider these estimates conservative. Satellites would face extreme radiation environments. Many would likely be damaged or destroyed. GPS navigation, on which everything from aviation to agriculture to financial transactions now depends, could be degraded or unavailable for extended periods. Communication satellites could fail. The internet, increasingly reliant on satellite links and vulnerable ground infrastructure, could experience major disruptions. The probability of a Carrington-class event is difficult to assess but not negligible. On July 23, 2012, a CME of Carrington-class intensity erupted from the Sun. By pure chance, it was directed away from Earth, missing our planet by approximately 9 days of solar rotation. Had the eruption occurred a week earlier, the CME would have struck Earth directly. Researchers estimate that the probability of a Carrington-class storm in any given decade ranges from approximately 10 to 12%, depending on assumptions about the solar cycle and CME frequency distributions. Over a human lifetime, the odds of experiencing such an event are substantial. Preparations have begun, but progress is slow and uneven. Some power utilities have installed GIC monitoring equipment and developed emergency procedures. NOAA and partner agencies have improved space weather forecasting capabilities. The Deep Space Climate Observatory, positioned at the L1 Lagrange point, provides 15 to 60 minutes warning of incoming CME arrivals, but fundamental vulnerabilities remain. The power grid has not been systematically hardened against extreme space weather. Many utilities resist expensive upgrades for an event that might not occur during their planning horizon. International coordination is limited. Standards are inconsistent. Richard Carrington died in 1875. Never knowing the full significance of what he had witnessed that September morning, he suspected that the solar flare and the geomagnetic storm were connected. But the physics that explains this connection would not be developed for another century. Today, we understand that he observed a pivotal moment in the relationship between the Sun and Earth, a reminder that our star is capable of violence that can reach across 93 million miles and shake our technological civilization to its foundations. The Carrington event was not unique. Ice core and tree ring studies have revealed evidence of even more powerful solar storms in the distant past. An event around 774 to 775 AD appears to have been 10 to 20 times more powerful than the Carrington storm. Another occurred around 993 to 994 AD. These Miyake events, as they are now called, would be catastrophic for modern civilization. We live in a technological age built on assumptions of stability that the Sun does not share. The Carrington event of 1859 stands as a warning, a historical data point demonstrating that extreme space weather is not theoretical speculation, but documented reality. The question is not whether another great storm will come. The question is when, and whether we will be ready. Chapter 7. The Sun-Earth Connection and Earthquake Theory. For over a century, scientists have debated a controversial question. Can events on the Sun, 93 million miles away, influence earthquakes here on Earth? The idea seems implausible at first consideration. Earthquakes result from the gradual accumulation of stress along fault lines, stress that builds over years, decades, or centuries until the rock suddenly fractures and releases energy. What could solar activity, operating on timescales of days to years, possibly have to do with this deep geological process? Yet the question refuses to disappear. It was first proposed as early as 1853 by the solar astronomer Rudolf Wolf, the same scientist who standardized sunspot counting. Since then, dozens of researchers have reported correlations between solar activity and earthquake occurrence. Just as many have published studies finding no connection at all. The scientific community remains divided. In recent years, new data and more sophisticated statistical methods have revived the debate. A landmark paper published in Scientific Reports in 2020 analyzed 20 years of proton density and velocity data from the SOHO satellite alongside worldwide seismicity recorded in the ISC GEM earthquake catalogue. The researchers found what they called clear correlation between proton density and the occurrence of large earthquakes with magnitudes greater than 5.6. With a time lag of approximately 1 day, the statistical significance of this correlation was striking. The probability of the correlation being a random coincidence was calculated at less than 1 in 100,000. Furthermore, the correlation strengthened as the magnitude threshold was raised. The largest earthquakes showed the strongest association with elevated proton density in the solar wind. If this result holds up to further scrutiny, it suggests that the solar wind is somehow influencing the timing of major earthquakes, not causing earthquakes from scratch, which would be physically implausible, but perhaps triggering the release of stress that was already accumulated and ready to rupture. Think of it as the straw that breaks the camel's back. The camel was already overloaded. The straw simply determined the exact moment of failure. What physical mechanism could explain such a connection? Several hypotheses have been proposed, and research published as recently as March 2025 continues to explore them. One hypothesis involves telluric currents. When the solar wind interacts with Earth's magnetosphere, it induces electric currents not only in power lines but also in the crust itself. These telluric currents flow through conductive rock layers, following paths of least resistance. Some researchers have suggested that these currents could heat fault zones slightly, reducing the frictional strength of the rock and making slip more likely. Others propose that the currents could directly stress the rock through electromagnetic effects. A second hypothesis involves the piezoelectric effect. Quartz and certain other minerals common in Earth's crust are piezoelectric, meaning they generate electric fields when stressed and conversely experience mechanical stress when exposed to electric fields. The reverse piezoelectric effect could translate variations in the electric field caused by solar wind disturbances into tiny additional stresses along fault zones. On faults already near the breaking point, these small additions might be enough to initiate rupture. A third and more recent hypothesis focuses on thermal effects mediated by the sun's influence on Earth's climate. Research published in 2025 by scientists from the University of Tsukuba and Japan's National Institute of Advanced Industrial Science and Technology examined how solar heat affects surface temperatures, which in turn influence rock properties and groundwater movement. Temperature changes can make rocks more brittle. Changes in rainfall and snowmelt alter the pressure on fault systems. While these effects are subtle, the researchers found that including surface temperature data improved earthquake forecasting models, particularly for shallow earthquakes most susceptible to surface conditions. The connection between solar activity and earthquakes may not operate through a single mechanism, but through multiple pathways acting simultaneously. Solar flares release bursts of X-rays and ultraviolet radiation that ionize the upper atmosphere. Coronal mass ejections send shock waves of plasma and magnetic field that compress the magnetosphere and induce ground currents. Variations in solar irradiance affect global temperatures over multi-year timescales. All of these influences interact with a complex Earth system that includes atmosphere, oceans, ice sheets, and the solid Earth beneath. Critics of the solar earthquake connection point to several challenges. The stress changes induced by any plausible electromagnetic or thermal mechanism are many orders of magnitude smaller than the tectonic stresses that cause earthquakes. How could such tiny perturbations trigger events releasing millions of times more energy than the perturbation itself? The answer may lie in the concept of criticality. A fault system near failure is exquisitely sensitive to small disturbances, just as a sand pile near its maximum slope can avalanche from the addition of a single grain. Another challenge is the difficulty of establishing causation from correlation. The sun exhibits cycles. Earthquake occurrence, while seemingly random, shows long-term patterns related to tectonic loading. Finding correlations between two complex, cyclical phenomena is relatively easy. Proving that one causes the other is far harder. Statistical flukes abound. Publication bias favors positive results. Researchers unconsciously choose parameters that maximize apparent correlations, yet the evidence continues to accumulate. A study published in Geophysical Research Letters in March 2025 introduced a new statistical method called shift neighborhood matching correlation to assess the link between intense geomagnetic storms and global strong earthquakes. The results indicated an increase in earthquake occurrence following geomagnetic storms, with the effect becoming apparent after a time lag that varied by region. 2025 has been an unusually seismically active year. Major earthquakes have struck in locations around the Pacific Ring of Fire and beyond. Simultaneously, the Sun has been producing some of the largest coronal holes of the 21st century, generating repeated high-speed solar wind streams that have buffeted Earth's magnetosphere. Is there a connection? The correlation is suggestive, but correlation is not causation. What is increasingly clear is that Earth does not exist in isolation. Our planet orbits within the atmosphere of an active star. Solar radiation heats our atmosphere and drives our climate. The solar wind shapes our magnetosphere and modulates cosmic ray influx. Geomagnetically induced currents flow through our crust, as they do through our power lines. We are embedded in a system where Sun and Earth interact constantly through multiple physical channels. The ancient intuition that events in the heavens influence events on Earth may contain more truth than modern science initially credited, not through mystical forces or astrological influences, but through well-defined physical mechanisms that we are only beginning to understand and measure. For earthquake prediction, the implications are potentially significant. If solar activity modulates earthquake timing even slightly, monitoring space weather could provide an additional tool for assessing seismic risk. Not a crystal ball that predicts exactly when and where an earthquake will strike, but a factor that elevates or reduces probability on timescales of days. Combined with other monitoring methods such as strain measurements, GPS deformation tracking, and seismic pattern analysis, solar activity data might improve our ability to issue meaningful warnings. Current earthquake prediction remains notoriously unreliable. Despite decades of research, no method has proven capable of predicting specific earthquakes with useful accuracy and lead time. The best we can do is identify regions at elevated long-term risk and issue warnings when unusual patterns appear. Any additional information that genuinely improves forecasting would be valuable. Research into the Sun-earthquake connection continues. The Chinese-Italian CSES Limadeau mission, launched in 2018, carries instruments designed to study possible influences of solar activity and ionospheric modifications on seismicity. A follow-up satellite is planned. Ground-based networks monitor electromagnetic anomalies that some researchers believe precede major earthquakes. Theoretical work seeks to identify the physical mechanisms that could link solar variability to crustal stress release. The jury remains out. Mainstream seismology continues to view the solar connection with skepticism, pointing to the many failed claims of earthquake prediction methods over the decades. Extraordinary claims require extraordinary evidence, and the evidence so far, while intriguing, has not reached the threshold that would compel consensus. But science advances by investigating anomalies, by taking seriously observations that do not fit existing paradigms. If there is a genuine connection between solar activity and earthquakes, ignoring it serves no one. The correlation found in multiple studies demands explanation. Either the statistics are flawed, or there is a real phenomenon that our models of earthquake physics do not yet incorporate. As coronal holes continue to open on the Sun, as high-speed solar wind streams continue to wash over our planet, seismologists will continue to monitor the ground beneath our feet. Perhaps one day, the connection will be understood and incorporated into earthquake hazard assessments. Or perhaps future research will definitively rule out any significant link. For now, we watch both the Sun above and the Earth below, aware that we still have much to learn about how our star and our planet dance together through space. Chapter 8. Touching the Sun with Parker Solar Probe. On Christmas Eve, 2024, humanity achieved something that would have seemed impossible to previous generations. A spacecraft flew through the atmosphere of a star. NASA's Parker Solar Probe, launched in August 2018, completed its closest ever approach to the Sun, passing just 3.8 million miles from the solar surface. To put this in perspective, Mercury, the innermost planet, never gets closer than 29 million miles from the Sun. Parker ventured nearly 8 times closer, plunging into the corona itself. that mysterious outer atmosphere where temperatures inexplicably soar to millions of degrees. At closest approach, the spacecraft was traveling at approximately 430,000 miles per hour, faster than any human-made object in history. At this velocity, you could travel from New York to Los Angeles in under 20 seconds. Parker was moving so fast that the sun's gravity could not hold it. The probe was on a trajectory that would swing it back out into the inner solar system before it returned for another close pass. The mission is named for Eugene Parker, the physicist who predicted the existence of the solar wind in 1958. When NASA announced the naming in 2017, it marked the first time the agency had named a spacecraft after a living person. Parker, then 91 years old, attended the launch in Florida the following year. He passed away in March 2022 at 94, having lived to see the first results from the mission that bore his name. The engineering challenges of building a spacecraft that could survive within the corona were immense. At 3.8 million miles from the solar surface, the Sun appears nearly 20 times larger than it does from Earth. Solar intensity is roughly 500 times greater. The sunward side of the spacecraft experiences temperatures approaching 1,800 degrees Fahrenheit. The solution was a revolutionary heat shield called the Thermal Protection System. This carbon composite shield measures about 8 feet in diameter and 4.5 inches thick. Despite facing extreme temperatures, the shield keeps the spacecraft body and instruments at a relatively comfortable 85 degrees Fahrenheit. The carbon foam of the shield is 97% air, making it surprisingly light while providing exceptional insulation. Behind the shield, 4 instrument suites gather data about the sun and solar wind. The FIELDS experiment measures electric and magnetic fields, radio emissions, and shock waves in the solar plasma. The Integrated Science Investigation of the Sun, with the acronym ISOIS, pronounced SOS, studies energetic particles accelerated by solar activity. The Solar Wind Electrons, Alphas and Protons instrument, or SWAP, directly samples the solar wind plasma, and the Wide Field Imager for Solar Probe, called WISPR, captures visible light images of the corona and solar wind structures. Parker has already transformed our understanding of the Sun. Among its most significant discoveries are structures called switchbacks, dramatic reversals of the magnetic field that occur abundantly in the near-Sun solar wind. These zigzag patterns, where the magnetic field suddenly flips direction before flipping back, were unexpected. They may hold keys to understanding how the corona is heated and how the solar wind is accelerated to its tremendous velocities. During its December 2024 close approach, Parker flew through the corona during a period of significant solar activity. Its WISPR camera captured stunning images of coronal mass ejections erupting from the Sun. In these images, published in late 2025, scientists observed something remarkable. Not all the material in a CME escapes the Sun. Some of it falls back. These inflows, as researchers call them, show elongated blobs of solar material raining back toward the solar surface after a CME passes. The phenomenon had been glimpsed from a distance by other missions like SOHO and Stereo, but Parker's extreme close-up view revealed details never seen before. The inflows appear to be magnetic field lines that stretched outward during the eruption but then snapped back, carrying trapped plasma with them. This discovery has implications for understanding space weather. If some CME material regularly falls back to the Sun rather than escaping, it affects the amount of magnetic flux and plasma that actually propagates through interplanetary space. It also means that CMEs reshape the solar corona in subtle but significant ways, potentially influencing the trajectory and intensity of subsequent eruptions. Parker has also investigated the mysterious heating of the corona. Why is the outer atmosphere of the Sun hundreds of times hotter than the surface below it? This question has puzzled physicists for over 80 years. Parker's observations point toward magnetic reconnection and wave heating as key mechanisms. The switchbacks it detected may represent magnetic field lines, reconnecting and releasing energy into the surrounding plasma. Alpha waves, oscillations that propagate along magnetic field lines, appear to carry significant energy outward from the Sun and may deposit that energy into the corona through various damping processes. The mission has made multiple passes through the corona, since first entering it in April 2021. Each approach adds to the dataset and refines our understanding. By flying through coronal holes, active regions, and the boundaries between them, Parker samples the diverse conditions that give rise to different types of solar wind. During one encounter, Parker discovered a surprisingly quiet zone within what was expected to be turbulent corona. A graduate student analyzing the data found regions where the magnetic field and plasma remained remarkably stable, even close to the sun. These calm patches within the storm raise new questions about the structure and dynamics of the inner corona. The spacecraft's journey to such close solar approaches required an innovative orbital strategy. Parker uses Venus gravity assists to gradually shrink its orbit. Over the course of the mission, it has flown by Venus 7 times. Each encounter bending its trajectory and dropping its closest approach to the Sun. The final Venus gravity assist occurred in November 2024, setting up the record-breaking December flyby. The orbit Parker now follows has a period of approximately 88 days. Every 88 days, it swings from a far point of about 0.73 astronomical units, roughly the orbit of Venus, down to its closest approach of 0.04 astronomical units, deep within the corona, then back out again. The spacecraft will continue making these close passes, with additional approaches at the same distance occurring in March and June 2025. Parker's primary mission concluded in June 2025 with its 24th orbit of the Sun. But the spacecraft remains healthy and continues to collect data. NASA is reviewing options for an extended mission that could continue operations for years to come, potentially gathering observations across more of the solar cycle. The data returned by Parker Solar Probe is not merely of academic interest. Understanding the Sun's atmosphere and the origins of the solar wind directly improves our ability to forecast space weather. Every CME that erupts, every high-speed stream that flows from a coronal hole, begins its journey in the regions Parker is now sampling. By understanding the physics at the source, we can better predict what will arrive at Earth days later. Future missions will build on Parker's achievements. The European Space Agency's Solar Orbiter, launched in 2020, carries remote sensing instruments that complement Parker's in situ measurements. At times, the two spacecraft have coordinated observations, providing multiple viewpoints of the same solar structures. This heliospheric Great Observatory approach, combining data from many spacecraft at different locations, represents the future of solar research. Plans are developing for even more ambitious missions. Concepts have been proposed for spacecraft that would hover in place above the Sun's poles. Impossible with current technology, but potentially achievable with advanced solar sails. Such a mission could continuously monitor the polar regions where large coronal holes form during solar minimum, providing early warning of high-speed streams before they rotate toward Earth. For now, Parker Solar Probe continues its lonely dance around the Sun, the fastest and among the most heat-resistant objects humanity has ever created. Each close pass brings new data, new discoveries, new insights into the star that gives us life. Eugene Parker lived to see his theoretical prediction confirmed by direct observation. The solar wind is real. Its origins in the corona are being measured for the first time. The spacecraft bearing his name has touched the Sun. As Noura Rawafi, the mission's project scientist, said upon confirming Parker's survival of its December 2024 flyby, "We are seeing atoms and molecules in the solar atmosphere colliding with our spacecraft. We are there. We have embraced a star." Chapter 9. Auroras and the Dance of Light. Stand on a dark night in the high latitudes, away from city lights, when the sun has been active and the sky is clear. And if fortune favors you, you will witness one of the most spectacular natural phenomena our planet offers. It begins as a faint glow, easily mistaken for distant city lights or the first hints of dawn. But this glow is green, not orange or white. It strengthens, it moves, and then, if the geomagnetic activity is strong enough, curtains of light unfurl across the sky, rippling and dancing in patterns that seem almost alive. The Aurora Borealis. The Northern Lights. The same phenomenon occurs in the southern hemisphere as Aurora Australis. The Southern Lights, Together, they are the polar lights, or aurora polaris, visible reminders that Earth exists within the influence of an active star. Humans have watched auroras for as long as we have lived at high latitudes. The earliest dated record comes from Chinese chronicles describing unusual lights in the sky, around 977 BC. Norse mythology attributed the lights to the Bifrost Bridge connecting Earth to Asgard, or to reflections from the shields and armor of the Valkyries. Inuit traditions speak of spirits playing ball with walrus skulls. Finnish legends call the phenomenon revontulet, meaning foxfires, from a story of an Arctic fox sweeping its tail across the snow and throwing sparks into the sky. The scientific understanding of auroras developed slowly. The term aurora borealis was coined by Galileo in 1619, combining Aurora, the Roman goddess of dawn, with Boreas, the Greek god of the north wind. But it was not until the 20th century that physicists unraveled the true mechanism. Auroras are caused by charged particles from the sun colliding with atoms and molecules in Earth's upper atmosphere. This basic statement contains layers of complexity that scientists are still working to fully understand. The process begins with the sun. The solar wind, that continuous outflow of protons and electrons, carries particles toward Earth at speeds ranging from 300 to 800 kilometers per second. When this plasma reaches our planet, it encounters the magnetosphere, the region of space dominated by Earth's magnetic field. Most of the solar wind flows around the magnetosphere, deflected like water around a stone in a stream, but some particles find their way in. Through the process of magnetic reconnection on the dayside magnetopause, when the interplanetary magnetic field is oriented southward, solar wind energy and plasma are transferred into the magnetosphere. This energy flows along magnetic field lines toward the poles, accumulating in the magnetotail on the night side of Earth. When conditions are right, instabilities in the magnetotail cause explosive reconnection events called substorms, releasing the stored energy and accelerating particles toward Earth. These accelerated particles, primarily electrons but also some protons, spiral down along magnetic field lines into the upper atmosphere at altitudes between 100 and 300 kilometers. There, they collide with atmospheric gases, exciting atoms and molecules to higher energy states. When these excited particles return to their ground state, they release the excess energy as light. The colors of the aurora depend on which atmospheric gases are excited and at what altitude the collisions occur. Green is the most common auroral color. It comes from oxygen atoms at altitudes between 100 and 300 kilometers. When an energetic electron collides with an oxygen atom, it can excite an electron within the atom to a higher energy level. This particular transition, from one excited state to the ground state, releases a photon of green light with a wavelength of approximately 557.7 nanometers. The excited state is relatively long-lived, about 3/4 of a second, which means the oxygen atom must avoid further collisions long enough to emit the light. At the densities found between 100 and 300 kilometers, this is usually possible. Red aurora appears at higher altitudes, typically above 300 kilometers, and sometimes as a lower border below the green. The high-altitude red comes from a different oxygen transition that produces light at 630.0 nanometers. This excited state is even longer-lived, requiring nearly 2 minutes to decay. At very high altitudes where the atmosphere is extremely thin, oxygen atoms can wait this long between collisions. The lower red border, when present, comes from nitrogen molecules. Blue and purple hues indicate nitrogen involvement. Nitrogen molecules, when struck by high-energy electrons, can become ionized, losing an electron. The ionized nitrogen molecule emits blue light as it recaptures an electron. Purple and pink colors result from mixing red oxygen emissions with blue nitrogen emissions. The patterns and movements of auroras reflect the dynamics of the magnetosphere. The basic structure is the auroral oval, an elliptical band encircling each magnetic pole at approximately 65 to 70 degrees magnetic latitude during quiet times. Within this oval, auroras are almost always present, though they may be faint. The oval expands equatorward during geomagnetic storms, bringing the lights to lower latitudes. Auroral forms range from simple arcs stretching east to west across the sky, to complex curtains, rays, spirals, and dynamic structures that can change within seconds. The most dramatic displays occur during substorms, when energy stored in the magnetotail is suddenly released. Aurora may fill the entire sky, dancing and flickering with an intensity that makes cameras struggle to capture the experience. The movement of auroras has a precise physical cause. The curtains and ribbons trace the magnetic field lines, along which particles are precipitating into the atmosphere. When these field lines shift, or when the region of particle precipitation moves, the visible aurora moves with it. The speed of apparent motion can exceed hundreds of meters per second. Waves and ripples propagating along auroral arcs reflect instabilities in the currents flowing through the ionosphere. Auroral sound is a matter of ongoing investigation and some controversy. Many observers report hearing sounds accompanying bright auroras, described as crackling, swishing, or hissing. Scientists initially dismissed these reports, calculating that sound waves generated at auroral altitudes could not reach the ground quickly enough to be heard in sync with visual changes. However, recent research suggests that electrophonic effects, where electromagnetic pulses induce vibrations in nearby objects like grass, hair, or eyeglasses, might explain some reports. The phenomenon remains not fully explained. The May 2024 geomagnetic storm produced auroras visible far beyond normal latitudes. The event, triggered by a series of coronal mass ejections, drove the KP index to 9, the maximum value. Aurora was observed from locations as far south as Florida, Texas, and Mexico in North America. And from the Mediterranean region in Europe, social media filled with photographs of red and green skies from observers who had never seen the phenomenon before. For communities at high latitudes, auroras are a regular part of life. In places like Tromsø, Norway, Fairbanks, Alaska, and Yellowknife, Canada, aurora viewing is a tourist industry. Guides lead groups into dark wilderness areas, equipped with cameras and warm clothing, hoping for clear skies and active displays. The combination of solar maximum conditions and northern winter darkness makes the current period particularly favorable for aurora tourism. Auroras are not unique to Earth. Any planet with a magnetic field and an atmosphere can produce them. Jupiter displays spectacular auroras at its poles, powered not only by the solar wind, but also by particles from its volcanic moon Io. Saturn's auroras have been imaged by the Hubble Space Telescope and the Cassini spacecraft. Even Mars, which lacks a global magnetic field, shows faint auroras in localized regions where crustal magnetic fields exist. Scientists study Earth's auroras using ground-based cameras, radar systems, and magnetometers, as well as satellite observations. The Themis mission, with ground observatories across North America and 5 spacecraft in orbit, investigates substorm dynamics. Citizen science projects like Aurorasaurus collect real-time reports from observers worldwide, helping researchers track the extent and intensity of auroral activity. For those fortunate enough to witness a major auroral display, the experience is often described as transformative. The scale of the phenomenon, filling the sky from horizon to horizon, the movement that seems almost intentional, the colors shifting and evolving, all combine to create a sense of connection to forces far larger than human concerns. In those moments, standing beneath the dancing lights, you are watching the sun's breath interact with Earth's magnetic armor. You are seeing charged particles that left the solar surface days ago complete their journey by exciting atoms in the thin upper air and releasing photons that travel the last 100 kilometers to your eyes in less than a millisecond. You are witnessing the universe at work, beautiful and indifferent, ancient and immediate. The aurora has danced over Earth for billions of years, since the planet first developed a magnetic field and an atmosphere. It danced before there were eyes to see it, before life emerged from the seas, before anything on Earth could wonder at its beauty. Now we watch, and we understand, and we are grateful for the show. Chapter 10. The Future of Our Stormy Star. The coronal hole that opened in December 2025 is not closing. If anything, patterns observed throughout this solar cycle suggest that we may see more and larger coronal holes in the years ahead, as solar cycle 25 descends toward minimum around 2030. This is the nature of the solar cycle. Activity rises and falls in an 11-year rhythm, but the descent is not a return to quiescence. The descending phase and the years of solar minimum bring their own forms of solar influence on Earth. Coronal holes expand and persist, particularly near the poles but also at lower latitudes where they can affect our planet. High-speed solar wind streams become recurring features of space weather, sweeping past Earth every 27 days as the same coronal holes rotate with the Sun. What can we expect in the years immediately ahead? Through late 2025 and into 2026, solar activity should remain elevated. We may not have reached the true peak of solar cycle 25. Some cycles exhibit double maxima, with a second peak of activity following the first by a year or more. Whether this cycle follows that pattern remains to be seen, but major flares, coronal mass ejections, and intense geomagnetic storms will continue to be possible throughout this period. By 2027 or 2028, a clearer decline should become apparent. Sunspot numbers will diminish. Active regions will become less frequent and less complex. But as the magnetic field simplifies, coronal holes will grow. The polar holes that persist through minimum can expand to cover significant fractions of the visible solar disk. Equatorial and trans-equatorial holes may become more common as magnetic field evolution creates open field regions at lower latitudes. These coronal holes will continue producing high-speed solar wind streams. While the peak intensity of geomagnetic storms tends to correlate with solar maximum and CME activity, the recurring disturbances from coronal holes during the descending phase and minimum can still reach moderate storm levels. Power grid operators, satellite operators, and aviation authorities will need to maintain vigilance. By 2029 or 2030, we should approach solar minimum, the quiet phase between cycles. Sunspots may disappear entirely for weeks at a time. Solar flares will become rare. Coronal mass ejections will diminish in frequency and intensity, but the heliosphere will change. With weaker solar magnetic activity, the bubble of solar influence surrounding our solar system will shrink. Cosmic rays from beyond the heliosphere will penetrate more easily, slightly increasing radiation levels at aviation altitudes and for astronauts in space. Solar cycle 26 will then begin, the next chapter in our star's magnetic evolution. Predictions for cycle 26 are not yet possible with confidence, as the forecasting methods that failed to predict the strength of cycle 25 demonstrate the limits of our understanding. Some researchers speculate that we may be entering a period of generally stronger cycles, ending the trend of weakening that characterized cycles 21 through 24. Others remain cautious, noting that solar behavior over century timescales is poorly understood. The longer-term future of solar activity contains deeper uncertainties. Some scientists have proposed that the Sun might be approaching a grand minimum, an extended period of very low activity similar to the Maunder minimum of 1645 to 1715. During that 70-year period, sunspots nearly disappeared. Whether the Sun can enter such a state again, and what the consequences might be for Earth's climate and space environment, remains debated. What is certain is that the Sun will continue its cycles for billions of years. Nuclear fusion in the core will gradually convert hydrogen to helium, slowly increasing the Sun's luminosity. Over hundreds of millions of years, this increasing brightness will affect Earth's climate in profound ways. Eventually, perhaps a billion years from now, the Sun will become too bright for liquid water to exist on Earth's surface. Life as we know it will face existential challenges long before the Sun exhausts its hydrogen and expands into a red giant. These deep future transformations are beyond human timescales. What matters for our civilization is the near term, the years and decades during which we must learn to coexist with a variable star. Space weather preparedness has improved significantly since the Quebec blackout of 1989. NOAA's Space Weather Prediction Center issues daily forecasts and alerts for geomagnetic storms, solar radiation storms, and radio blackouts. A fleet of satellites monitors the Sun and the solar wind, providing data for forecasting models. The Deep Space Climate Observatory at the L1 Lagrange point offers 15 to 60 minutes warning of CME arrivals. New satellites launching in the coming years will add further monitoring capabilities, but significant gaps remain. Warning time for the most extreme events is measured in minutes to hours, not days. The ability to predict exactly which CMEs will be geo-effective and how strong the resulting storms will be remains limited. Many power grid operators lack real-time monitoring of geomagnetically induced currents in their systems. Standards for space weather resilience vary widely between countries and between industries. The European Space Agency is developing the Vigil mission, planned for launch around 2031. This spacecraft will be positioned at the L5 Lagrange point, trailing Earth in its orbit around the Sun. From this vantage, it will observe the Sun from the side, detecting active regions and CMEs before they rotate to face Earth. This could extend warning times significantly, providing days of advance notice for some events. Research continues on improved forecasting models. Machine learning techniques are being applied to the wealth of solar data accumulated over decades. Magnetohydrodynamic simulations model the propagation of CMEs through interplanetary space with increasing realism. Coupled models connect solar observations to magnetospheric response to ground-level effects. The goal is forecasting that rivals terrestrial weather prediction in accuracy and lead time. Meanwhile, efforts to harden critical infrastructure proceed unevenly. Some utilities have installed GIC blocking devices on vulnerable transformers. Some satellite operators have developed procedures for safe mode operations during extreme events. Some governments have commissioned studies on national resilience to space weather. But progress is slower than the science would suggest is prudent. The next Carrington-class event will come. Whether in 10 years or 100 years, the Sun will eventually produce a storm of that magnitude, and if it is directed toward Earth, our technological civilization will face a test unlike any it has experienced. The Quebec blackout affected one province for 9 hours. A Carrington event could affect continents for months or years. Preparing for such an event is not alarmist. It is rational risk management. We prepare for earthquakes, hurricanes, and pandemics. We should prepare equally for the certainty that the Sun will occasionally remind us of its power. For those of us watching the Sun in 2025, the immediate future offers both challenges and opportunities. The giant coronal holes appearing during this solar maximum are previews of what the descending phase may bring in amplified form. Each high-speed stream that washes over Earth teaches us something about the Sun-Earth connection. Each geomagnetic storm tests our monitoring systems and response procedures, and each aurora that dances across the sky, visible from latitudes that rarely see such displays, reminds us of the connection between the fire burning 93 million miles away and the thin envelope of atmosphere and magnetic field that makes life possible on our small blue world. The Sun has burned for 4.5 billion years. It will burn for 4.5 billion more before swelling into a red giant and shedding its outer layers. Compared to these timescales, human civilization is a brief flicker. Yet in our brief moment, we have developed the ability to understand our star, to monitor its activity, and to begin protecting ourselves from its hazards. The dark wound on our star, the coronal hole staring at us from December's sun, is both a threat and a teacher. It threatens our satellites, our power grids, our communication systems, but it also teaches us about magnetic fields, plasma physics, and the fundamental processes that govern stars throughout the universe. We are students of a restless star. The classroom is dangerous but magnificent, and the lessons, if we pay attention, might just help us survive the next great storm. The wound remains open, the wind continues to blow, and we continue to watch, to learn, and to prepare for whatever our stormy star sends our way. If you enjoyed this deep dive into solar activity and its effects on Earth, please like this video and subscribe to the channel. Your support makes these detailed explorations possible. Tell me in the comments which space weather topic you would like to explore next. The May 2024 superstorm, the history of solar observation, the future of space weather forecasting. The universe is vast and full of wonders. Our sun is just one star among hundreds of billions in our galaxy alone. But it is our star. Its light warms our world. Its storms challenge our technology. Its mysteries call to our curiosity. Thank you for watching. I will see you in the next investigation.